All right. Morning, everyone. Welcome. So not really too much logistics to talk about. The only thing I guess I'll point out is, so if you can push up to office hours, always great, love that. Generally, the biggest benefit of that is I get to see the challenges that the people are facing. The biggest challenge does seem to be right-hand rule. Right-hand rule seems to be the major challenge. And there is a question on the quiz. There's a question on the quiz where you'll have to find the force on a moving charge. And I give you an X, Y, Z plane, and I tell you the direction of the motion, magnetic field, and all that jazz. That question is really going to test if you know right-hand rule. And there's something very important you all need to know concerning the force on a moving charge. It is that the force is always 90 degrees to the direction you're moving and to the magnetic field. The force is always 90 degrees. When we do right-hand rule, the reason we do our right hand in this way is our thumb is 90 degrees to the direction of the velocity. When you do a thumbs up, your thumb is 90 degrees. If your thumb is bent at even a slight angle, that is going to mess things up. So that is a very important idea that happens when you do right-hand rule. The force is perpendicular to both the direction you're moving and the magnetic field.
So the thumb is DL or DV?
So this is specifically for the quiz that's this week, which is force on a moving charge. So there's two right-hand rules. The one I am referencing is right-hand rule number 1, which is the force in a moving charge. Then right-hand rule 2 is what you use to find the magnetic field. So two different rules.
Oh, you were just describing the first one.
I was describing the first one, yeah. The other thing you all need to know is that the force on a negative charge is opposite. Remember, negatives always do the opposite. If you ever see a negative charge in a problem, it will do the opposite of what a positive charge would do. Always. If you remember the rules for positive charge, you just flip it for negative. And that every single thing in this class, that's going to be the case. All right. Now, last class, we did the force. We did finish up the force slides. And then we started talking about how do you make a magnetic field. And we said, what experiences a force to a magnetic field? Current carrying wire. So what makes a magnetic field? A current carrying wire. A moving charge. And we introduced something called Biot-Savart's law, and I told you you're not ever actually going to use this integral. So I showed you all the slide for Biot-Savart's law. I said, don't worry about this integral. We are going to use it to derive some expressions, and we derived one of those expressions last class. This was the magnetic field due to an arc of wire. Now, an arc of a wire basically, it needs to be a circular piece of wire. It could be a full circle, half circle, quarter circle, third of a circle. An arc is specifically a piece of a circle, and we are only finding the magnetic field dead center. If you want to find the magnetic field anywhere that's not dead center, it's much worse, which is why I'm not going to have you do it.
I theta, that's it?
It's mu naught I times theta over 4 pi r. Yep, where theta is the angle of the arc, and this must be in radians. We practiced it. We had 2 quick questions at the end. I said, hey, if you have a half loop, what's the equation going to be? And in that case, theta equals pi. I then had you find the direction. And we use right-hand rule number 2 to do this. So right-hand rule is the new rule. Right-hand rule 2 is where you put your thumb in the direction of current. And there's two ways I told you to do it. One, put your thumb in the direction of current and imagine a circle going around the wire. And that your fingers are going to tell you the direction of that circle. Find a point, tangent to the circle, gives you the direction. The other one was point your thumb in the direction of current. Point your fingers at the point, your palm points in the direction of the field. And you can see as my thumb traces this path, my palm always points outward. All right. Now, I then gave you all, I think I was able to get to this. Actually, this is looking like the wrong PowerPoint. So I was like, why is this so complete? All right, I didn't get to this next slide, so let me open up the right one. My studio class tends to get a little bit further because we have a little bit more time. So we did find the direction of that arc. I am now going to teach you all a shortcut for right-hand rule 2. Right-hand rule 2 is used to find the magnetic field. This shortcut works for any loop or any piece of a loop.
Did you show us this already?
I may or may not have shown it to you. I don't know. I don't have any drawing on here currently. So this is right-hand rule 2.5, because it's like a shortcut for right-hand rule 2. This only works for loops of wire, but it's very easy. It's very convenient. Take your fingers, curl them in the direction that the current is going. Which way is my current going? Clockwise. What's the direction of the field inside it? Into the page. So this is a shortcut for any loop. Now, when I say loop here, this could be a square loop, a circle loop, an oval loop, a crazy-looking, lumpy loop. What's important is it's a loop. Loop means that it closes in on itself. In fact, you could even do this with the last problem. This last problem, you can do the same thing. Even though it's just a piece of a loop, the same rule applies. Curl your fingers towards the current, and your thumb gives you the direction of the field inside. Only inside the loop. This little shortcut only works for loops, and it only works inside the loop. So in this case, what does the magnetic field look like inside? It is going to be into the page. Everywhere inside this, the magnetic field is going to be into the page. It's not uniform. It's not the same value everywhere, but it does point the same direction everywhere. Everywhere inside is going to point into the page. Now, the next question we're going to ask is, what does it do outside of the loop?
Can you show that previous example one more time?
Yeah, so this previous example, just take your fingers, curl them in the direction the current's going, and inside, if you imagine this was a loop, inside of it, it points out, just like we got before. Okay, now, what does it do outside the loop? A very important thing with magnetic fields, and I think we've seen this in a previous PowerPoint with like the Earth's magnetic field. I'm just going to Google a picture of it real quick. You all have seen pictures of magnetic fields. In your all's middle school, elementary, high school, I don't know. You probably saw it several times. You've probably seen pictures of the Earth's magnetic field. So, Earth's magnetic field. These are just generic pictures. Any one of them works. Notice what the magnetic field lines do. They all make these circles. We've been seeing this the entire time. Magnetic field lines always make circles that close in on themselves. Always. All magnetic fields loop back on themselves. That's just a rule with magnetic fields. The reason is because every magnetic field has like this dipole thing. It's just a law. It's an observation of reality. Why do magnetic fields do this? It's just how the world works. You all have seen this here. You all have ever played with bar magnets? Bar magnet, magnetic field. You all have seen this picture. I guarantee this shouldn't be something like new. Middle school, high school, elementary school, at some point you've seen these like field lines. All of these arrows loop back on themselves. Every single magnetic field line made by any possible object in the entire universe loops back on itself. That's a rule. It's an observation of reality. How do you prove this? How do you observe this? You take a magnet, you like sprinkle some iron filings around it, and they line up with the field. The way you can visualize a field is just have a bunch of tiny iron particles, and they'll line up with it. So, why do I mention that? Why is that fact getting said? If we consider this loop, so here this loop is kind of flat. I tilted it sideways so we can see the entire magnetic field from the side. So same loop, but like tilted on its side now. Do the right-hand rule to find the magnetic field inside. So we're going to curl our fingers with the current. And this loop is kind of flat on the page. Inside, which way does the field point? Down. So based on that logic I just told you, if that magnetic field is going to curl back on itself, what's it going to do? We can do right-hand rule on the outside of it, and we'd find on this side it points up. How do I know that? If you just applied right-hand rule, put your thumb in the direction of current. On the right side, it's into the page. My point's to the right of it. My hand points up. This is the normal right-hand rule. So if I connect these together, this is what the magnetic field lines look like around a current-carrying wire. They make these big old loops, big old circles. And which way do these circles go? On the inside, they go down. On the outside, they go up. And down here they go sideways, up here they go this way. So this is what the magnetic field looks like through a loop of wire. Why do I mention this? This should look very similar to pictures I just showed you. Specifically, this looks a heck of a lot like the Earth's magnetic field. And so why does it look like the Earth's magnetic field? Just an interesting fun fact for you all. The current theory is that in the middle of the Earth is a big iron core with a bunch of charge on it. When that core is spinning, I have spinning charges. What are spinning charges? Current. What does the shape of a magnetic field look like? Through a loop of current spinning in a circle. The thing that we just drew. So the Earth is just, at the center of the Earth is a bunch of current spinning in a circle because there's an iron core that's charged and it's spinning really fast. There's a movie called The Core. It's a really slightly corny, it's a sci-fi movie that's super old. It was like on the Sci-Fi Channel way back when. The whole premise of the movie was, oh no, the Earth's core stopped spinning, the Earth's magnetic field stopped, and they tunneled to the middle of the Earth and stopped moving. It's ridiculous, but the idea of the Earth's magnetic field being generated by a spinning core is accurate.
How come, can you back to the picture for a second?
Yep.
How come the bottom arrow is the bottom arrow?
Oh, that's one that one's wrong, thank you. One of them's wrong, one of them's right. Good catch. There we go. Yeah, they should make a closed loop one-way path.
Could you go over the different hand rules that you use to get the top and the bottom, the spiral?
Oh, the spiral, I just connected the loop. I just if this side is down and the right side is up, I got to connect them together with some circle. If you want it, yeah, it's a good question. If you want the magnetic fields down here, it gets a little complicated because you kind of have to do all of these with wire. But if we just pick this right side of wire, I can put my thumb out of the page. And my fingers point down, so they'll point down here, and then my magnetic field will point to your right. Yeah, so you could just take a piece of wire and it gives you a pretty good sense. The closest piece of wire will give you a good sense. All right, so this is what the magnetic field looks like around a loop of wire. It looks like the Earth's magnetic field. It looks like a bar magnet. It's just kind of interesting connections here. Now, why do bar magnets make magnetic fields? That's a longer answer. The very, very quick answer for you all is that what do electrons do? Electrons, to very simplify this, electrons orbit an atom. Oh, I've got a moving charge moving in a circle. What is that? A current going in a circle. So you can think of atoms as just a bunch of currents swinging around them. More complicated is that electrons themselves also make magnetic fields. They have something called spin. Any of you that are physics majors will take quantum mechanics. You'll learn about spin. The rest of you, you'll hear about as much as I just said. It's not often mentioned too much. That's a good question. Do we generate current? You're right. There is currents going on, specifically. Oh, this is biological. A lot of the signals in your body are chemical, though I believe some are electrical. Which ones are which? I honestly don't know 100%. There is an electrical signal made to trigger your heart, but I think most of the signals are through a chemical. Yeah, there's a combination. I think there is some current going in your brain, and so they do generate small amounts of magnetic fields. But I know very little about the extent of that. All right. Okay. Let's go ahead and solve a problem with this. So, I don't think we've done this yet. This is the first time. I want you all to think back just to connect this to a problem we've done before, because that's how all learning is done. If I gave you two charges, and I said, find the electric field at some point, try to remember how you would solve this problem. This is way back, this is from the test one. Two charges, find the electric field. How do you do it? You find the field due to one of them, you find the field due to the other one, and you combine them. Why do I mention that? So find the field due to one, find the field due to two. We cannot just add these willy-nilly. We got to break them into components, add them together. This is something you've done. What I need you to now connect in your brain is that a current-carrying wire is kind of like a point charge. A current-carrying wire is like a point charge. Why do I say that? If I can break this problem into 4 geometries of wires, then I can treat it kind of like quote-unquote 4 point charges. I can find the field due to each segment of wire and then add them together. Now, the segments of wire we're going to consider in this class are straight lines and arcs. So I want you all, you're going to break this into 4 pieces. See if you can figure out what 4 pieces you're going to break this into. I'll give you all a few moments for that, then I'll show you what that answer is. How can I break this into 4, quote-unquote, independent pieces? All right, so the 4 pieces are going to be, there's a straight piece in the bottom. I haven't taught you the magnetic field due to a straight piece of wire, but don't worry about it for now. We're going to see why we don't really care. So we're going to call that wire 1. We're then going to call this top arc wire 2. Notice I'm drawing the direction of current on each arc. That's an important thing that we need. Then I'm going to do wire 3. That's going to be the straight piece of wire down here. And then we're going to have the arced piece, and that's the last piece. So I've broken this wire into 4 pieces. This is a rule that you all need to be very comfortable with, specifically being able to take a complex problem and break it into small pieces that you can work with, and then learning to recombine them later. Every single complex problem in your entire life is just a bunch of simple steps strung together. What makes something complex is how many steps are involved that you have to string together. Think of anything in your life, and that's how, even walking seems like a simple motion, but there's a lot of things going on. It maybe looks simple from the top, but the amount of muscles moving and your ankle muscle, like so many joints and things moving. Anyway, it's a bunch of simple things strung together. All right, so we're going to look at the easy ones first, specifically the magnetic fields due to I1 and I3. Because these are kind of in line with this, I haven't taught, we can kind of sort of try to do right-hand rule. I put my thumb in the direction of current, and it's just not even possible to put my finger over there. Like, remember, what's the magnetic field look like due to a straight wire? It's a circle going around it. It's a circle going around it. That circle never really hits that point. So the magnetic field, due to these straight pieces of wire, because they line up with this point, because this point isn't above it or below it, because remember this magnetic field's doing like this circle, that circle never really intersects it. So what's the magnetic field due to wire 1? 0. What's the magnetic field due to wire 3? 0. So we basically ignore it. The only reason we put those straight wires was so that we could have a closed loop of current.
Sorry, why is it 0?
It's 0 because it's a good question. And I kind of hit it. The magnetic field makes a circle around it. If we imagine that circle around it, that circle doesn't really exist on the wire itself. Yeah. And if we pretend like this wire kept going, you don't have a magnetic field on the, just like a charge can't make a field where it's at, a wire can make a field where it's at. So we can almost like pretend like this wire continues down. Kind of hand waves us past that. Alright, now the arc of wire we have learned, and my first question to you all before we do any math is I need you to find the direction of the field at point P due to each of these arcs. So find the direction of the magnetic field due to the bottom arc, arc 4, and then find the magnetic field, the direction of it due to I2. Arc 4 goes counterclockwise, arc 2 goes clockwise.
Wait, why is it 0?
Because it's a straight wire, it's in line with the wires. If you're in line with the wire, the field's 0. We'll just use that as our hand waving. Alright, so we're going to use, I'm going to do it both ways. I'm going to do it the official way, quote unquote, right-hand rule 2, and then I'll do it the shortcut way. What's the shortcut way? Point your thumb in the direction of current, point your finger to the point, and your palm points in the direction of the field. You can see as I trace this, my palm always points outward. I keep my fingers pointed towards P, my palm always points outward. So the magnetic field to the current carrying forward is outwards. You want to do the shortcut way? Curl your fingers in the direction of it. Oh, I get the same exact answer outwards.
Wait, do we have to make sure like the palms of our thumb is like facing outwards?
So right-hand rule 2 says it depends which one you're doing. Right-hand rule 2, you point your thumb in the direction of current. You point your fingers towards the point you care about. Thumb in the direction of current. Finger in the direction of the point. Palm points in the direction of the field.
Okay, so for I2.
Right there, same thing. My current now is going up to the left. Up here, my current is going to the right or to the left, so on and so forth.
I know there's just certain cases where we like twist our like not all the way.
So you just gotta, this one, right hand rule 2 is a flat hand. Right hand rule 2 is a flat hand. Right hand rule 1 is a different rule entirely. So this is defined in my magnetic field. Alright, current carrying wire 2. We're just gonna do the shortcut way. Curl your fingers in the direction of it and point into the page. Great. Why did we do this? If we do not know the directions of the fields, we cannot determine how to combine them. Remember the example I gave you all from test 1. We had to draw the directions of them so you knew how to combine them. In this case, we had to break them into components because they're not parallel and anti-parallel. And the problem I just gave you, we are blessed. They're anti-parallel to each other. Why is that convenient for us? We can just subtract them from each other. I'm going to go ahead and make the executive decision that out of the board is positive, into the board is negative, because that's most people's intuition tends to fall in that camp. Okay, so if I want, so let's just actually evaluate this. What is the equation for the magnetic field to an arc of wire? Mu naught I theta over 4 pi r. Why is it that equation? Because I derived it last class. Now, in the case of both of these wires, it's a half loop. So what's my angle? Pi. So in the case of B2, sure, we'll do that one first. It really doesn't matter the order. I have mu naught I times theta 2 over 4 pi r2. I'm putting it all in general, and then we actually plug in the values. Mu naught times I times pi over 4 pi times b. Wire 2 is a distance b. The angle is pi because it's a half loop. I is I because it says so in the problem. Yeah, that's it. Where did I get the I from? The current in this entire loop is I. In series, the current's the same everywhere. So every single piece of the wire gets the same current. If there are different wires, that might not be the case. Using the exact same logic, just for the sake of time, I'm not going to write it out. Wire 4 is just replace B with A. Still a half loop. Yeah.
So the angle is just the shape then?
Yeah. Okay. The angle is how much of a circle do you have?
Okay.
In this case, we have half a circle. So the angle that half a circle traces out is pi, because it's in radians. If it was a quarter of a circle, it'd be pi over 2. If it was a full circle, it'd be 2 pi. It's a great question, yeah.
Where is the magnetic field for 2 be negative?
That's a great question. For now, I haven't defined the sign yet. I'm going to define the sign when I add them together. In fact, to make that a bit more clear, I'm just going to put magnitudes here, just to make it maybe a bit more clear. The reason I'm not putting negatives now is I like to put negatives when I add them together. If I put negatives in both cases, you might accidentally cancel out the negatives. So let me write this out and then I'll answer that question there. So B net is going to be B1 plus B3 plus, in this case, B2 is going to be negative. Why? Because we defined it negative is into the page. Plus B4. So if you add these together, we get mu naught I over 4 pi. They both have mu naught I over 4 pi. And we get 1 over, and I'm running out of room, so I'm being a little stingy here. Yeah. Negative 1 over, no, I'll write this out. I'll be kind to you all. I'm being stingy on space, but I don't need to be. I'll give myself a bit more room by just making it a little bit smaller. Okay. So B net therefore equals 0 plus 0 plus mu naught I times pi over 4 pi b with a negative sign in front, plus mu naught I pi over 4 pi times a. If you factor out all the constants, we get 1 over b minus 1 over a. Nope, other way around. 1 over a minus 1 over b. All right. Yeah. Does the I cancel? Pi. No, it should be there. But we can cancel it out on the top and the bottom. Yeah.
So you define negative as not like the direction of the current, but as like...
We're adding vectors. So what's our end goal here? So the question is a good question. How do I define negative? What are we adding? We're adding the magnetic field vectors. This is an arrow pointed into the page and an arrow pointed out of the page. I'm adding two arrows. One's in one direction, one's in the other direction. If I add two arrows that are pointed in opposite directions, they're going to cancel each other out somewhat. Maybe not completely, but they're not going to get bigger. They're going to kind of subtract from each other.
It's going to be zero. But if it was higher or lower than it?
Correct. That's a great question. The question was, what if point P was a little bit higher? This problem would be awful. If this point was a little bit higher, we'd have two problems. One, the straight wires would contribute in a way that we're going to learn in just a little bit. Also, if it was a little bit higher, we couldn't use the equation for an arc of wire. That only works in the dead center of this quote-unquote circle. So, two problems there. Yeah?
Why is Q1
Why is B1 and B2? B1 is the magnetic field due to the straight wire, it's 0. And B3 is a straight wire, and that one's 0. So I just, yeah. Now, we're blessed in this problem because we didn't have to break into components, but don't get in the habit of just adding fields and assuming that they always just add. In fact, let me show you all a problem in the problem set. There is several where that is not the case. So in your all's problem set, there is, I gave you all, basically most of this problem set is find the field due to a bunch of different wires and add the fields together. So when I pop it open, you're going to see what I mean. So scroll. All right, so find the magnetic, here's a long straight wire. We're going to learn the equation for this in a second. I say, hey, this wire makes a magnetic field. There's already another magnetic field. You need to add them together. This wire, what will be the direction of the magnetic field at some point above it? Go ahead and just do right-hand rule real quick. You do know how to do this. Find the direction of the magnetic field above this wire. Some random point above the wire. It says specifically 20 centimeters above. Some point P. Found in the direction of current. It makes a circle around it. Which way does the circle point above it? Out of the page. Why am I mentioning this problem? There is an existing field that's down. If you want to combine a vector that is out of the page and a vector that's down, how do you do it? Pythagorean's theorem. They are 90 degrees to each other. They are vectors. How do you combine vectors that are 90 degrees to each other? Pythagorean's theorem. Do not get in the bad habit of just adding vectors willy-nilly. You've done a lot of vector addition in this in Physics 1. Components matter. Yeah? Yep, the current goes left to right. So meaning the current, you can see the picture goes to the right. That's a magnetic field. That's a random magnetic field that exists for reasons undefined. Yep. But yeah, this entire problem set. Oh look, find the magnetic field due to this arc, and I got some straight wires. Find the magnetic field due to two arcs. Find the magnetic field due to two straight wires. Find the magnetic field due to two straight wires. Why did I give so many examples of this? The more combinations I give you, the less you'll be surprised if I give you. You'll have seen a bunch of different versions. What does this very likely mean? Very likely one of the free responses is going to be, hey, here's a bunch of wires. Find the magnetic field at some point away from them. If I give you this many problems doing the same process in a bunch of different scenarios, that probably means I really need you to know the process. And this is not something you can memorize. You cannot just memorize the equation for two straight wires or a straight wire and an arc. It is so easy for me to make so many different versions of this. A half loop and one straight wire, a half loop and two straight wires, a quarter of a loop and three straight wires. You need to know the process. This process, though, is just find the field due to each piece and then add them together. Break them into X and Y if you have to. All right. Next thing I need to teach you all is the straight wire. We learned an arc. Now we're going to learn a straight wire, and that's going to cover 95% of cases. Most things can be defined as a straight wire or an arc of wire. All right, so we're going to derive it, and when I say derive it, we're going to build the integral, and then I'm going to say, pretend like we did straight stuff and solve it. And we are going to do this for a finite wire. This is the equation that will be on your formula sheet, not this one, but the solution to this. So, I'm going to keep that picture because it's already on another slide, it's fine. All right, by Savard's law, I am not going to spend a long time on this. I'm going to go very quick. I do not need you to know the derivation, but I want you to see it doesn't come out of thin air. If you're a physics major, you will derive this in one of your upper level courses. It'll be a homework problem or a test problem or something. All right, great. I am trying to find the magnetic field at some point P above a finite wire. How are we going to do this? The same way we've been building our integrals. First step, draw a picture. Next step, pick a small piece of wire. Pick a small piece of wire. What are we going to call that piece of wire? DL. Tiny, tiny little piece. Now what are we going to do? The same thing we've been doing as well. We're going to draw the distance from that thing to the point. We're going to label that R, because that's what we've been doing. This is not anything. It should kind of look similar to things that you've seen before as far as building integrals. Okay, now what are we going to do? Oh, and I'm going to make my life a little easy. I'm going to make the origin at the point. It's just, you'll see why it makes my life a little easier. Okay, there's my integral. That's what we're starting with. Next step, what do we do after we draw a picture? Oh, actually, let's put the angle here. That's generally helpful. Okay, what are we going to do now? We write our integral. Great, it's already written for us. Now what? We're going to write this a little nicer, and I'm going to give myself a little bit more room by shifting this to the left. Trying to shift it to the left. All right. What does the cross product turn into? The cross product turns into, and I'm going to pull out my constants because I'm allowed. They're constants. What does my cross product turn into? The magnitude of the vectors. This r hat is the direction of r. What's the value of r hat? 1. So the magnitude of r hat is 1, so it's going to just disappear. But whenever we do this cross product, here, in fact, I'll write it for you all just in case you look at this later. The value of r hat is 1. That's always true. Okay, sine theta. The angle between those is sine theta. Next thing we do, the same thing we didn't do, and we're going to change dl. We're going to integrate over this wire. If this wire goes left-right, what variable are we going to turn dl into? dx. Great. See, you've done this. dl is going to turn into dx. So we're going to have mu naught over 4 pi integral of I dx sine theta over r squared. Now, we do need to find the direction of the field here because we need to determine whether or not to break this into components. Generally, when we do these additions, we got to break this into components. How are we going to find it? Point your thumb on the direction of current. We're going to just pretend like this point's right above it. We don't even need to turn around. We're just going to pretend like the point's right above it. Which way does the field point? Out on the page. What if I pick the wire over here? We just do the exact same thing. We pretend like the point's right above it. Also points out. So no matter where you pick on the wire, above it, the field's going to point out. No matter what pieces you pick. Why is that important? I don't need to break it into components. They all point out. If they all point out, we can just add it up. Now, I am going to pick another piece of wire here just to show you all something that's going to maybe look a little weird. I'm going to do something a little weird. We're going to take this angle, and if I take this angle and I sweep this arm, so this is the angle currently between my elbow and the straight wire. I want you to track where that elbow, we're going to keep using that same angle as we sweep over the wire. So this is the angle, this is the angle, this is the angle. The angle, as my arm moves, stays on the outside. That's important for this derivation. This angle is going to stay on the outside for this problem. That's going to be important for us doing this. So I want to show you all that now.
What is mu naught?
Mu naught is 4 pi times 10 to the minus 7. Yep. All right. Now, r is changing. Theta is changing. So what would be my next steps? My next steps is that I would write r in terms of this distance. Let's just call it d. What is r squared going to equal? It's going to equal the square root of x squared plus d squared because I chose my origin very nicely to make my life easier. This distance on the bottom is x. It's a triangle. If the bottom is x and the vertical is d, x squared plus d squared equals r squared. Great. Okay, what else could I do? I could replace sine of theta with opposite over hypotenuse. What's my opposite side? D. What's my hypotenuse? R. We then plug this in and we get an awful integral. We get the integrals that we kind of saw with Coulomb's law. I'm going to go ahead and show you all. So this is the one where we kind of left it off. The I sine theta dx, I pulled it out. How do you solve this integral? We don't actually solve it in terms of x. We do trig sub. And you can look at this in your own time if you want to, but it's just doing trig sub like we did before. I'm not going to spend the time on this because it's not worthwhile. It's just trig sub though. R here is D. In fact, here, let me put that on this picture so that they're similar. So if you're really curious on this, you can spend the time and look at this. But it's like this, it's trig sub. Yeah. Sorry, what's your question? Oh, great point. Yep, this should not be a square root because it's squared. Yeah. So on the bottom, though, you would get an over r cubed and, trig sub. All right. The end result of this trig sub is this equation at the bottom. And I have it here nicely for you all. And I need to point out something very, very important. So it's u dot I over 4 pi r. R is the constant. Where does that come from? Doing the integral. But what's important here is this angle. So we use cosine of theta 1, where theta 1 is this angle down here. It's the angle between the wire and kind of this R, this line from the left wire to the point. That's theta 1. Theta 1 is a number. It will be given. You will have to either figure it out in the problem, but it's a set value. It's from the leftmost point to that, make a triangle, find that angle. Theta 2, and this is the thing I want you all to be careful of. Theta 2 is not that angle. It's not the inside angle. It's this outside angle. That's very, very, very important for you getting the right answer. Why is it that outside angle? Because I showed you all like my arm sweeping across it, that theta. When I go from here, my angle theta turns into that one. That angle that's on the right side of my elbow stays on the right side of my elbow. Okay, and then it comes from the derivation and how we do trig sub. Okay, you do not need to know where this equation comes from, but you do need to know how to apply it. You do need to know how to apply it, and so we're going to do a few problems on that now. Specifically, we're going to first look at the extreme. What if I take one of these ends and I take it to infinity? What does the angle turn into? How do I go from a finite wire to an infinite wire? So, let's go ahead and practice that. Here's the picture. Theta 1 is this angle on the bottom left. It's the angle between the leftmost piece of the wire and this like dotted line that reaches the point I want to find the field at. If I took this left piece of the wire and I stretched it all the way to infinity, what does my angle turn into? Does the angle turn into 0, pi, pi over 2, 2 pi? We're going to do this one, and then we're going to do the other side. Does this angle get bigger, smaller, stay the same?
Why the wire use like the radius?
Yeah, so this wire, if it's like finite, has endpoints. Like it, if this is a finite wire, it has endpoints. And so theta 1 is the angle between this endpoint and this dotted line that's next to point P. So that dotted line, I'll just draw another random wire. Say here's a wire. Say I have some point P here. That's theta 1. No, the dotted line is not moving. Yeah, That's why theta 1 is a number. That's why it's a set value. It's a set value depending on your problem. Yep. It's because it's specifically, this is locked on the left side. Whereas when you do a theta 2, it's locked on the right side. Yeah. It's not sweeping along it. These are the bounds of my integral, this theta 1 and theta 2. Yeah. No. They're the same value, but 2 pi is an angle that sweeps all the way, so it's mathematically the same, conceptually not the same. If that makes sense.
Because I know that they are the same value, but
if you based on how this angle is drawn and defined. Yeah. Mathematically, it'll get you the same result, but conceptually, it's like you jump through some hoops. All right, give y'all 10 more seconds. All right, in 5, 4, 3, 2, 1. So the idea here is, what if we made this wire, if we stretch this in? This dotted line is attached to this end. This dotted line here is attached to that end. So as I stretch this line, as I stretch the left side of the wire to infinity, that dotted line gets flatter and flatter and flatter and flatter. How do we know it gets flatter? Look, you can see an example here. When it's closer to it, it's bigger. You can see a random spot that's closer is bigger. So, let's just draw some examples here. If my wire was only this big, that's my theta 1. If my wire is now this big, that's my theta 1. As I stretch this wire out, it gets flatter and flatter and flatter and flatter. And what's the flattest you can possibly get? It's 0. When you're infinitely far away, the angle turns to 0. Because it's just stretched. Kind of try to visualize that. All right. Now, while 2 pi technically gives you the correct answer, cosine of 2 pi does give you the same as cosine of pi. Based on the picture, 2 pi is not a visually correct angle here. This angle should get smaller and smaller and smaller, not bigger and bigger and bigger. So that's why 2 pi is not what theta 1 turns into, even though mathematically it will turn out the same. All right, let's do the other side. What if theta 2? What is theta 2 if the wire is infinite? Now, very, very, very important that you all remember, this is not theta 2. Theta 2 is not the inside angle. Theta 2 is that outside angle on the right side. If I stretch that wire to infinity, what does that angle turn into? Both directions, it doesn't really matter. We're caring about the right side here. Yeah, the question is, if the wire is infinite, we looked at theta 1 already. If the wire is infinite, the right side also stretches to infinity. Both sides stretch to infinity. We're theta 2, and they all say theta 1. Go ahead and copy and paste. Yeah, they should all be theta 2. Theta 2, theta 2, theta 2, theta 2. All right, we'll close this out in 15 more seconds. And 5, 4, 3, 2, 1. So, as my right side stretches to infinity, what happens to my arm? As I stretch to infinity, this arm also gets flatter and flatter and flatter and flatter. But we're looking at the outside angle. What happens to what's the outside angle for a flat thing? It's going to be pi. Now, we can plug these values in to derive the expression for an infinite wire. So if we use our expression for a finite wire, our expression for a finite wire is mu naught I over 4 pi r times cosine theta 1 minus cosine theta 2. Let's plug in the values. You all just told me that theta 1 is 0, theta 2 is pi. These are nice numbers. What is the value of cosine at 0? It's 1. What's the value of cosine at pi? -1. You can see why it's important for us to choose that outside angle. 1 minus -1 is 2. So we get 2 mu naught I over 4 pi r. 2 over 4, that simplifies nicely to mu naught I over 2 pi r. That is the equation for an infinite wire. Currently, that equation is not on the formula sheet. On the formula sheet, I give you an arc of wire. I give you a finite wire. An infinite wire, you can either derive when you need it, or write it on your 5x8 note card. Up to you. It's a good thing to be able to derive, though, because it really tests if you understand this theta 1 and theta 2. It's not a hard derivation. You just plug in 0 and pi, and it spits it out. Doesn't mean I want you to necessarily do it on the test, but it does mean I need you to know this theta 1 and theta 2. So great, there it is.
I don't understand how it's pi.
How it's pi?
Yeah.
If this wire is flat, if this point is flat, what's this angle? It's going to be 180 degrees, which is pi.
Wait, what?
This line is getting flatter and flatter and flatter. This angle is from the line to a flat part. What's the angle for a flat? So it might be one you have to kind of draw out. Yeah, so 180 degrees is pi in radians. Yeah. All right. Finite wire. Okay. Let's make sure we're paying attention regarding vectors. At some point, b1 equals 3x hat. At some point, b2 equals 4y hat. What's the magnitude of that field? Is it 1 Tesla, 3 Tesla, 4 Tesla, 5 Tesla, or 7 Tesla? Oh, there is no picture. Yeah, this is its own problem. Yeah. Yeah, this is different than that one. But it uses the same idea. All right, give you all about 20 more seconds. November 6th. Yep, so... That's on the same way. Because I just got this question twice, it's a good question therefore. Remember the exam is November 6th. Thursday, November 6th is our next exam. When is November 6th? 3 weeks from today. 3 weeks from today. We're going to roll. We got 2 more weeks to cover things. I got Ampere's law to cover. I got Faraday's law to cover. And maybe one day on AC circuits. All right. 5, 4, 3, 2, 1. All right, this looks pretty good, and this is just seeing if you remember their vectors. 3x is to the right with the value of 3. 4y is 4 upwards. What's my net force? Or not force. This is not force. What's my net magnetic field? It's the hypotenuse. So it's going to equal 3 squared plus 4 squared. It's a 3, 4, 5 triangle. It's the best triangle. All right. Why did I do this? Do not get in the bad habit of always just adding your fields together or subtracting them. Remember, these are vectors. Draw the vectors. Draw the picture. If you do not draw your vectors, you will make this mistake of doing 3 plus 4 and thinking that's the net field when it is not. It does not matter what discipline you are going into. You're going to be working in 3 or more dimensions. If you're a computer science major, you're like, I'm not going to work in 3 dimensions. You're right. You're going to work in much more. It's going to be even worse for you. Everyone else, 3 dimensions. If you cannot be cool with 3 dimensions, you're going to have a hard time. All right. Speaking of multiple dimensions, here's a problem. We're going to see that happen. I got 2 straight wires. 2 infinite straight wires. They are parallel to each other. They both point into the page. They are 20 centimeters apart, and I say find the field at some point halfway between them and 5 centimeters up. How do you solve this problem? Draw the field to each of these wires at that point. That is your first step. Okay, well, first step, what are we solving for? B net. Second step, draw the arrows. If you are not drawing the arrows, you have a very high chance of making a mistake. This is very hard to hold in your head. Very hard to hold in your head. And when you draw this picture, add the numbers to it. Notice I didn't add them to the picture for you. Why? I want you to do it. And it's very important for you all to draw pictures with dimensions on them. All right, so I'm just going to draw these values real quick. And it's 0.2 meters on the bottom. It's 0.05 meters up. Convert your units sooner than later. If you wait, you will mess it up. And I saw in the test in the first response, converting units is definitely something that gets forgotten. Do not forget to convert your units. This distance here will be 0.1 meters. That's honestly the one that we're going to use. In fact, I'm just going to draw that one by itself, so it's a little bit cleaner. All right, so great, I got that. Let's draw some fields. How do we do this? 1 wire at a time, just like we did 1 charge at a time. Pretend like the other one doesn't exist. Point your thumb in the direction of current. Pretend like it makes a circle around it. It does make a circle around it. What's the direction of the circle at that point? Down to the right. It is not to the right. It is not up. How can I prove that to you all? By drawing a circle.
Why is it into the page?
The current is into the page. And what does the magnetic field look like around a current-carrying wire? A circle. So, one way is drawing this circle. And what's the tangent line at this circle? Down to the right. What's the other way of doing this? Thumb in the direction of current. Finger towards the point. Which way does my palm point? The exact same way I do the field. down to the right. Why does it point down to the right? Because it's a circle, and I'm somewhere on the top right of that circle. You can see that in the picture here.
I got confused from like what the palm and thumb represents. Like the thumb is the direction of the current.
Thumb is the direction of current. Keep your hand, so you got to pick one of the two ways. Either you're spinning your hand to make a circle, or you're doing the short area. I'm just going to recommend the quick way because that's the easier way to explain. Flat hand, thumb in the direction of current, fingers towards the point, palm points in the direction of the field. That's right hand rule 2. Thumb in the direction of current, fingers towards the point, palm points in the direction of B. So that's B1. Do the same process for B2. Wire 2, thumb in the direction of current. Again, I'm going to use the easier one because it's easier to explain, even though it doesn't give you the full picture. Thumb in the direction of current, which is into the page. Don't make a mistake of exiting out of the page like I almost just did. Thumb into the page, point is up here, palm points up to the right. Why? Because it makes a circle around it and it's tangent to that circle.
So the palm represents the
Direction of the field. Alright, now my arrows here, I ideally should have drawn them the same size. Symmetry. They are the same distances from the point. They have the same current. That is the only thing that affects the field, is the distance and the amount of current you have in this type of wire, both straight wires. Why does that matter? These are not in parallel or anti-parallel. We're going to have to break them into components. But if you realize there's symmetry, what's going to happen to the Y component? It's going to cancel. We can prove that mathematically in just a bit. Now, I can get B1 and I can get B2 very easily. What's the equation for an infinite wire? Mu naught I over 2 pi r. Why? Because we already derived it. That's for an infinite wire. That's true. Both of these are infinite wires. So, if I want B1, if I want B2, it's very easy for us to get those values. So I'm going to make a new slide, copy everything over. This problem is a fairly simple version of these problems. But what it is testing is, do you know how to find directions? Do you know what to do when there's multiple wires? I do not expect you all to be able to do this super simply right now. We're just practicing it for the first time, but I am telling you this is an easier example. So, B1 is going to equal mu naught I over 2 pi r. Now my r here, I1, R1. How do I find the value of r? Very easy. Square root of 0.1 squared plus 0.05 squared. So if I want B1, it's going to be 4 pi times 10 to the minus 7 times the current. The current is given in the problem as 5 amps. 5 amps. I'm not going to put the A in there because that gets confusing. Over 2 pi times the square root of 0.1 squared plus 0.05 squared. Great. You plug all that in, you'll get a number, and that's going to give you B1. B2 is the exact same equation. Same current, same distance. B2 is the exact same thing. Mu naught I2 over 2 pi R2. It's the exact same thing. 4 pi e to the minus 7 times 5 over 2 pi times the square root of 0.1 squared, 0.05 squared. Great. What does that equal? I'll plug it in real quick. So 4 pi times e to the minus 7 times 5 divided by 2 times pi times square root of 0.1 squared plus 0.05 squared You're like, why is he saying it out loud? Saying it out loud actually makes it more likely you're plugging in the right numbers. I've just found that for myself. So that's going to equal 8.94 e to the minus 6 Tesla. I am not going to just add these numbers together and call it a day, because that's bad. You have to break it into components. If I want to find B net, I need to find B net in the x direction. I need to find B net in the y direction. How do I do that? Angles. This theta. So I'm going to copy all this over to another page real quick. I'll just shrink things. It'll be fine. Great. Now it's shrunk. All right. You want B net in the x direction? Find B1x and add B2x. Why am I adding them together? They both point to the right. How do I add them together? I'm going to do 8.94 e to the minus 6 times cosine of the angle. Why cosine? Because that's going to give me the x component. Now, do I need to solve for the angle and then plug it in? That's one way of doing it. Another way of doing it is remembering the definition of cosine. What is the definition of cosine? Cosine equals adjacent over hypotenuse. That is the definition of cosine. Adjacent over hypotenuse. So you could just plug that definition in there and hit enter and get the equation. So, I'm going to take that, move it on down.
Did you forget a negative?
No, they're both positive because they're both to the right.
Oh, it just says the...
No, it has to be e to the minus 6. You just have to...
Oh, thank you. That negative. Yes, I did lose the negative. Thank you for catching that. All right. You get the exact same thing on the other side. So you just multiply it by 2. I would not write this out myself, but I'm going to write it out so you all can see this, but they're the same value. If this was me plugging this in, I would have just multiplied it by 2. And yeah, it's really fun to plug in. Hopefully I've convinced you all that numbers are unpleasant to work with. And it's much nicer when we just work in variables. It's the physicist way.
Oh, that should be 0.05, right?
Yeah, thank you. 0.5 squared, great. And that comes out to 8e to the minus 6. Great. Make sure I did all the things. Great. Cool. All right. What's going to do the y component? The y component's 0. Why? You can do the math yourself if you want to. Use sine instead of that. They both get the same angle, but one's up, one's down. They subtract each other, equal and opposite. I'll let you do that. I'm not going to spend the time on it because we don't have the time. It's not very interesting. All right, so the answer is 8e to the minus 6 Tesla to the right. Great. All right, so what's the takeaway? Just like every other vector we've talked about, you can add vectors by breaking them into components and adding them. If you can just break this into a bunch of pieces that you can work with, then you can add all those pieces together. And basically, any problem I give you will be a combination of straight wires and arcs of wires. That's really the only permutations I can give you. Technically, I can give you solenoids, but So look, here's one that has both. I'm not going to solve it completely for the sake of time, but I will kind of set up. I got a straight wire, infinite straight wire going into the page. I got an arc of wire, specifically an entire loop. Find the magnetic field at the center of that loop. It says the radius of the wire is r, and the straight wire is a distance 2r from the center of the loop. So, first step, what are we solving for? The net magnetic field. You should always write down the variable you're solving for, because if you can do that, that gets you so far. If you don't write that down, you might be solving for the wrong thing. Next, draw the direction of the field due to each of these situations. Which way does the field point at point P due to the straight wire? Which way does the field point at point P due to the circular wire? Draw both of those. Go for it. I'm going to label my variables on here because that's a good practice. We'll do that as well. Oh, that's a good question. Does it not say? Clockwise. Yeah. It doesn't show in the picture. You got to draw it. That's a great point. You got to figure out the direction it's going. It is not shown in the picture, but it is said in the wording. Make sure you know what direction clocks go. I'm very curious how long it'll take the next generation. At what point generations won't know why clockwise is defined the direction it is. It will. I'm almost confident it's going to happen at some point. That analog clocks are going to disappear. And people, it's just, it's how things go. There's a lot of things like that. Like if I send a page to someone, no one knows what that means nowadays. Pagers haven't existed for so long. Alright, so let's do the straight wire. Straight wire we're going to call 1. Circular wire we're going to call 2. It's convenient. Straight wire. Thumb into the page, fingers towards the point, magnetic field points down. Remove my little R here so it's not in the way anymore. Magnetic field due to wire 1 points down. Due to the loop of wire, you're going to use a shortcut because it's nice. Curl my fingers around, my magnetic field points into the page. What does this mean? It means I have two vectors that are perpendicular to each other. So when you calculate these, you cannot just add them willy-nilly. You need to add the squares and square root it. If you do not draw these, you will not realize that. And if you do not realize that, you will get it wrong.
How did you come to that conclusion? Did you point your thumb into the direction of
Wire 1, thumb goes in, finger towards the point, palm points down. So that's for magnetic field due to wire 1.
Right, no.
Wire 2, curl my fingers in the direction of it, thumb points in. That's the shortcut for a loop of wire. So, the B to the wire is going to be really straightforward. It's an infinite wire, so it's mu naught I over 2 pi r. Now, you need to be careful here. This is not the magnitude of the magnetic field due to the infinite wire. Why? How far away am I from this wire? I am not a distance r. I am a distance 2r. Yeah, it's a good, at the bottom of the question, and that's why you always want to draw your distances on your picture. It might have been better if I'd put capital R, capital 2, capital R, but it doesn't actually change anything. All right, great. You all want the wire due to the arc? It's going to be mu naught I times theta over 4 pi, the radius of that wire. Now, that one is just R. But what's my angle? My angle is 2 pi. Why? Because it's a full circle. So great, I got my two fields. You can simplify them a little bit. Add the squares of them. And you get the net field. So this one actually I will work out. I mean, it's pretty easy at this point. I don't have to plug in numbers, so it spares me a lot of suffering. Us physicists love not having to plug in numbers. The really cool thing is in engineering, if you can make the equation, you can just plug in the numbers into a computer and they'll do it for you. I mean, a calculator is just a computer, right? All right, so the b to the wire. So if I want b net, it's going to be the square root of the b wire squared plus the b of the arc squared. Why? Because they're perpendicular to each other. That is unique to this problem. The b to the wire, I am going to simplify things. So it's going to be the square root of mu naught I over 4 pi r. All of that is squared. Plus this other one, I'm going to get mu naught I. The pi's are going to cancel. The 2 is going to cancel that. Oh, yeah, that's supposed to, I don't know why I did that. Yeah, good catch. Mu naught I over 2i. Okay? And now we can just pull out, this simplifies really nicely. The mu naught I, they both have that in common. They both have a 2 in common. They both have an r in common. So what's left in the inside? 1 over pi squared. 1 over 2 pi squared. Plus 1. So it simplifies pretty nicely. Yeah, it's a great question. Why did I not break it into components? These are already perpendicular to each other. They are purely perpendicular to each other. So how do I add vectors that are purely perpendicular? I add the squares of their magnitudes. If I have an arrow to the right and I have an arrow up, how do I combine those vectors? Pythagorean's theorem. In the last example, there was actually only the x. We were adding vectors that were not parallel to each other or perpendicular, so we had to break into x and y. The y component canceled. All right, not going to do that one. All right. We got 3 minutes, so I'm going to hit y'all with this one. All right, so to put what we learned last week and what we learned this week, to put those two pieces together, current carrying wires make magnetic fields. Why? We just spent this whole week talking about that. Current carrying wires experience forces in magnetic fields. Why? Because they do. That's how the world works. So what happens if I have 2 wires, both carrying a current that are near each other? One will make a field. The other will experience a force due to that field. One wire will make a field. The other experiences a force due to that field. Remember? 2 positive charges. What's going to happen? One makes a field, the other experiences a force due to that field. Wires are the same way. So, here's the problem for you all. This is what we're going to close out with. I have 2 parallel wires. They both carry current straight up. What is the direction of the force on the second wire? But why is there a force? Because the first wire makes a field here. So this is a 2-step problem. Find the field at point P due to this other wire. Now I have a magnetic field here. Find a force on this wire due to that field. Find the field, then find the force. Wire 1 makes a field. Wire 2 experiences a force due to that field. Wire 1 makes the field. Wire 2 experiences a force due to that field. You need both right-hand rules to do this problem. Yeah, let me write out this little strat, and then I'll send it out. Yeah. Find the field at P due to 1. Find the force on 2 due to this field. Yeah, but thank you for reminding me of that. I realized that as I was writing the instructions, but otherwise I might have missed it. Is the force on that wire up, down, into the page, or left? And I'm not asking for the direction of the field at point P. I'm asking for the force on the second wire. I am asking for the force on the second wire. All right, for the sake of time, because we're at time, I'm going to solve this while leaving it open. Wire 1 points up, so what's the direction of the field at point P? Into the page. Now I have a field. Now we're going to use right-hand rule 1. Point your fingers in the direction of current. Swing them towards the field. The force is to the left. This is how this was discovered. This is the experiment that defines even what an ampere is. It's how much these deflect when you have two wires carrying the same current a certain distance apart. So the answer is to the left. They get attracted to each other. If they were anti-parallel, they get repelled. If the currents are going in opposite directions, they would get repelled. Yeah, I'll close it out, but yeah, thank you. I'm leaving it open so everyone gets it right at this point. Hey. Oh, 1 second.